We now consider the displacement vector. The displacement vector is the change in the position vector of a particle. Its symbol is given the symbol for change, which is a triangle, and then it tells you what it's changed. It's the position vector. Or if you're doing in one dimension, 1D problems, books generally just say delta x. Now, the formula for the position vector comes directly from its definition. Delta r delta r is defined to be the second position or final position vector minus the initial position, or sometimes in books written as the first position. Notice there's the r, the subscript 1 meaning the initial, and the subscript 2 meaning the final position. So find the final position vector, subtract the initial position vector, that gives you the change in position vector, which is called the displacement. The units of this is meters, the units of that position vector are meters, so the change has the units of meters. So displacement vectors, units are meters. We can look at this graphically. Here I have a ball here. The ball initially was right here, and it was given by this vector r1. Let me mark that a little bit, maybe brighter, make it easier to see. There it goes. And then after some time, the ball is moved to a second position, and we can show that with this vector right here. So it's now right there. That's its final location. So the question is, where is the change? Well, it's really something that you do all the time in everyday life. You're here, you want to go to there, so how would you walk? You'd walk like this. So that is the change in the position vector. So that's all you have to do graphically. Now if you look at that from working with coordinates, we could say, hey, the coordinate y right here for my blue vector is delta y, which is y2 minus y1, and its x coordinate, delta x, is simply x2 minus x1, and we could go back and put that into our formula. So we could say, but you can also say this is delta x I hat plus delta y j hat. And if you were to do it in, for instance, 3 dimensions, there would be a delta zk hat. This is actually a more general statement because you can work in coordinates other than just Cartesian. But you'll find this very useful in the chapters 3, especially in working problems. Now, what else can we find out about this displacement vector? Well, let's do an example, see if we can work just a straightforward problem, and then we'll talk about its difference between it and distance. In this example, it says a baseball is initially located 50 feet from the batter at a height of 5 feet. So that will be this point right there. That's point 1. Ball's right located there. 50 feet. And over here it's 5 feet in the Y. And then some later time, the ball moves to a new spot right here. Call that point 2, which is located at 30 feet along the X, and it's located 4 feet along the Y. I'm going to go ahead and write those two vectors down. R2 is 30 feet I hat plus 4 feet J hat, and R1 is 50 feet I hat plus 4 feet, oops, I'm sorry, 5 feet J hat. So what's delta R? Well, delta R is found by taking the 30 feet in the I hat and subtracting the 50 feet. So 30 feet minus 50 feet along the X, that's delta X, and taking 4 feet and subtracting 5 feet along the Y. So delta R, the displacement, is minus 20 feet I hat minus 1 foot in the Y. And that's the answer to this problem. That's the displacement. And if we look at that, we see it's a vector that goes like this. It goes over 20 feet this way, so it's going in the negative X direction, just like math said, and the ball fell. So the ball came, for instance, the batter's right here, the ball is coming toward the batter, and the ball is also dropping. Now, something else to notice about this, again, if we play around a little bit, in general, delta R is R2 minus R1. So if we solve that for R2, we find that's R1 plus delta R. And you can see that in the diagram. There's R1, you add delta R to it, and you get R2. This is vector addition. So the displacement vector is the vector you have to add to the initial position vector in order to get to the final vector. So if you don't like to think about it subtracting, you can work it and rearrange it so that you think about it as vector addition. And that's what this little box here in your note says. Graphically, the displacement vector is the vector you have to add to position vector 1 to get to position vector 2. Now, a very important fact. Displacement is not the same thing as distance. Distance is a scalar quantity and is always positive, while displacement is a vector quantity, and so you can add two displacements and end up with 0. If you walk two distances, first in one trip and another, you won't get 0. Let me show you that by an example. We have a runner here, and this runner is going to start here at point A, and then it's going to walk to point B, and that's going to take it 100 meters. And then after it does that, it's going to turn around and going to walk back to get back to point A. And during that time, it's going to walk a distance of another 100 meters. And the question is, well, what's the distance that the runner covers? Well, the answer is 100 meters plus 100 meters. The amount of distance you walk is 200 meters. This is what people do all the time. Unfortunately, it's not distance but displacement that's important in physics. Therefore, we need to really understand vectors. If you're talking about one dimension, this vector is walking 100 meters I hat, which is positive, but because it's a vector, this is a minus 100 meters in the I hat. So they'll end up at 0. Another way of thinking about this is, if you started here at the green dot, and then you closed your eyes, the runner ran over here and ran back, and then you opened your eyes and you see them at the same place, you couldn't tell the difference that they'd even moved. This gives you their displacement. The displacement is 0. This is the only time, by the way, that you can put a vector equal to what looks like a scalar. 0 in vectors means no x component and no y component, no z component, or any other component. So these are not the same thing. Velocity, which we'll get to later, is defined by using the vector displacement. It's not defined in terms of distance. Do two observers measure the same displacement if they use different coordinate systems? It appeared, if all you're doing is adding a constant, as we were in Logger Pro, that would have the same displacement because the constant would get subtracted out. However, in that case, it was because the two coordinate systems were not moving with respect to each other. Let us look at a more general case. In this place, I have put a cart that is moving to the right. Tom is shown with his coordinate system in red, while Sue has attached her coordinate system to the cart. As the cart moves to the side, like this, we can see that Tom will see that the cart has actually increased to a higher value of x. Let's say that we measure the position being the front of the cart. So there was the initial value, maybe it was 4 meters. But later on, the cart is at some new location. Let's say it's 9 meters. So Tom would say that there was a displacement of 5 meters in the I hat direction, assuming that Tom says that's the x. But for Sue, if she measured on her axis this distance to be 2 meters, then when the cart gets over here, the distance will still be 2 meters. So Sue, because she's attached to the cart, would think that the cart has no displacement whatsoever. Again, assuming she defines that to be the x. So if two observers are moving relative to each other, they will not agree on displacement, just as they also may not agree on position if their coordinates were not aligned. So this means that the displacement can be different, and therefore two observers can measure different velocities. Sue, for instance, could believe the cart is stationary, while Tom believes that the cart is moving to the side. We see this all the time on planet Earth. To us, the Earth is stationary, and we treat the Earth as stationary when we make measurements and drive and walk. But to a person who is watching us from outer space, they would see, in fact, that the Earth is moving around the Sun at a very high speed and is, in fact, spinning on its axis. Again, you have to define the coordinate system to be able to make measurements in physics.